Hello, in this video I'm going to give you just a kind of a quick crash course review of the subatomic particles in an atom and tell you a little bit about some of their facts. Also give you a little bit of a background on how we handle some really basic but important statistics or facts about the elements on the periodic table. So it probably wouldn't hurt to have your periodic table handy, or any periodic table really, but the one that I've given you in class or that you'll receive in class soon is the one that I'll refer to in most of the videos throughout the year. So subatomic particles have to do with all the pieces then that are inside of the atom, the smaller than the atom particles, subatomic. And you're not going to have to know this sort of historical trivia about them necessarily, but I just wanted to kind of show it to you. Just to kind of remind you that we didn't always know all this about the atom. The electron was the first particle discovered around 1897, depending on how you make these dates official, but it was the first one sort of officially understood. The proton came later, about 20 years later, and then the neutron after that. All these discoveries happened sort of centered around the same lab area, which was actually in Cambridge, England, or in England at the University of Cambridge. And here's a picture of an entrance to the lab, I guess one of the labs at the University of Cambridge. So these three particles, all discovered within a relatively short period of time, really changed how we understand the atom for sure. And understanding the atom made chemistry possible the way that we study it today. So just some real quick biography about the subatomic particles. Subatomic particles include the proton, neutron, and electron. As I mentioned, the proton's basic facts: the proton is positive. Its symbol is P, lowercase p, with a little plus sign on it. It has a mass that we call 1 AMU, or atomic mass unit. The atomic mass unit is a very generic sounding term, but it's the name that we give the unit that we use to measure the mass of an atom. Because using things like grams is incredibly difficult for things this small. Protons and neutrons, electrons all have masses that are so impossibly tiny in terms of grams that to talk about them in terms of grams would give us some really small and really unwieldy numbers. Something on the order of 10 to the negative 24 grams. That's just beyond our comprehension. So to simplify things a bit, we use the atomic mass unit to describe the mass of an atom. And so an atom will have a mass in not some tiny amount of grams, but in some typically whole number of AMUs. The charge on a proton, as I mentioned, is positive. It has a positive charge. We won't get necessarily at this point in this course into why protons have a positive charge. That gets a little further down the rabbit hole than we need to go. Protons, hopefully you remember from 9th grade, are found in the nucleus. On the other hand, neutrons, which are another heavy particle in the atom, they also have a mass of 1 atomic mass unit, are neutral. They don't have a charge at all. So neutrons are neutral, and we write them as lowercase n with a small 0 above them. So from now on, anytime you want to refer to the proton, just go ahead and write p with a lowercase, or p with a plus sign, and then neutron, a lowercase n with a 0 to talk about neutrons. You don't ever need to write the word proton or neutron again if you don't want to. They have a mass of about 1 AMU. It turns out the neutron's mass is about, well, I shouldn't say about, it's slightly larger than that of a proton, but the difference between them is so inconsequentially small that we don't get into it. It's found in the nucleus along with the proton. So both of the particles that have a heavy mass, which are the proton and neutrons, are found in that nucleus of the atom. The electron is the other particle, of course, and probably the most important one, the one that you'll hear most about throughout the class. Electrons get a lot of the top billing, even though they're the smallest particle. They officially have what we call a mass of 0 AMUs. Now, they're a particle. They're a subatomic particle, so they do exist. They are a real thing. They're hard to understand, but they do exist. So they actually do have a mass. Their mass is actually so much smaller than a proton and a neutron that we just say it has a 0 mass. It's around 1,840 times smaller than a proton or a neutron would be, and so its mass is considered rounded down essentially to 0. It would take so many electrons before they would even add up to 1 AMU that no atom would have that in its size. And frankly, very few molecules that we would work with in our class would have that many electrons. And once you've got that many electrons, you've got that many protons and neutrons as well. And they just so dominate the mass that it's a little bit, I always tell students, think about an electron and its mass like taking a small sticker off of a piece of fruit and sticking it on the side of a bowling ball and imagining that bowling ball would suddenly feel heavier in your hand. The electron's mass is like that sticker on the bowling ball. Yeah, it counts, but compared to the bowling ball, it's so inconsequential that you won't even notice that it's there. Its charge is very important, however. Its charge is -1. And that charge, of course, balances out with the proton or cancels out the proton's charge. And it's that balance of proton and electrons, the number of positive versus the number of negative particles in the atom, that will help us to understand the atom's overall net charge, whether it has a net charge, and how that charge interacts with other charges to make bonds, to form compounds, to attract or not attract to certain other particles. Electrons are found out in the electron cloud, so they're in that very sparse region around the heavy, tiny, dense nucleus. The nucleus of the atom is where all the mass that matters is found, the protons and the neutrons. It's where all the positive charge is found in that nucleus with the protons. The electron cloud is super large by comparison and contains nothing but electrons whose mass is practically zero. So imagine, the way that I've seen it described is to think about a large professional, say, football stadium or college football stadium. The nucleus would be like a small pebble on the 50-yard line, right in the middle of the stadium. That's where all the mass would be concentrated. That's where all the positive charge would be concentrated with the protons and the neutrons there. And the electrons would sort of exist throughout the rest of the stadium, the furthest out of them, as far away as the outer reaches of the stadium. So all the mass of that large space would be concentrated in a tiny point in the center of the stadium, or in the center of the atom. So an atom's mass is very unevenly distributed, and its negative charge is then spread all around that outermost region. Okay, we're going to move on to what's called atomic number and mass number. So atomic number is a key piece of statistical data or information about any atom at all. The atomic number is equal to the number of protons in an atom. And with anything else in this video, if this is stuff that you remember from having learned it prior in 9th grade, perhaps, most likely, or even before that, and you just remember it well, you don't need to write notes down all this stuff. The key is you're responsible to be able to know all this stuff. So if you know it all and you wouldn't miss any of these ideas, then don't feel like you need to write it all down. But if you're like, man, I would kind of forget some of these little important details, then by all means put it down, and we're going to make you practice a little bit to show us that you know it, or to help you remember the things that you maybe learned prior, just to get them fresh again in your head. So listen along, but don't feel like you need to write everything. The atomic number is equal to the number of protons in the atom. So that's it. That's the bottom line. In the case of platinum here, we see the atomic number shown as the 78 in the corner. On most periodic tables, the atomic number will be the most prominent number, typically the largest font on the block for that element. In this case, we see it in the top left corner. That's not always where it's going to be, but it'll be a whole number, and it'll be typically very prominent. Most periodic tables will include the atomic number, and some will include nothing else. Just the atomic number and the symbol, perhaps, would make a periodic table. The mass, which is coming here in a minute, is not always included. In fact, our periodic table doesn't show mass number at all. Atomic number, again, found as the most prominent piece of information, is a key identifier of the element. So to talk about platinum is to talk about its 78 protons. Those things are inseparable. When you're talking about an atom with 78 protons, it must be platinum, period. And every single platinum atom out there has 78 protons, period. Those are completely overlapping things. There's no separating an atom that has 78 protons and saying, most of them are platinum, but this one's something else. No, if it has 78 protons, it's platinum, end of story. If you change the number of protons, it can no longer be platinum in this example. So that's a really key identifier. Neutrons can come and go and change and vary, and it's still the same element. Electrons will come and go easily. They will come and go. They will be taken from other atoms. They will be lost to other atoms or ions. And the atom may still remain its same identity, in this case, again, platinum. And we'll see lots of examples of that. Now, mass number is simply a matter of counting up all the particles that have mass that counts. And as I mentioned here a minute ago, that's the protons and the neutrons. So for mass number, we're looking at counting up the number of protons plus the number of neutrons and just adding those together. Protons plus neutrons, period. So, for example, here, a carbon atom that has 6 protons, 6 electrons, and 8 neutrons would have a mass number of, well, add those two things together. We've got 14 total protons and neutrons. 6 protons, 8 neutrons gives us a total of 14 particles with mass. And so we would say that that carbon atom has a mass of 14 AMUs, or a mass number of 14 AMUs. It's often described or sort of notated in the way that you see here, and that is to say, I would call this atom a carbon-14 atom. and I would write it as carbon-14. So when you see an element written out this way, carbon-14 or uranium-238, that's telling you the mass number of that particular atom of carbon or uranium, and so on. So it's a way of showing it. We don't show the AMUs in that case, but that when it's written in that format, carbon-14, it's implying that that's an atom of carbon with 14 AMUs. And from there, we can figure out how many protons and neutrons that atom would have. Now, carbon comes in what we would call 3 different forms or isotopes. Those 3 different isotopes have 3 different mass numbers. And isotopes, in the case of atoms then, are simply atoms of a particular or given element that have a different mass number due to varying numbers of neutrons. So if I change the number of protons, I've made a new element. If I've changed the number of electrons, and we'll talk about that here in a minute, I haven't changed the element, I've changed its charge, its balance of protons with electrons. But if I change the number of neutrons in an atom, I've affected its overall mass number because neutrons contribute to mass number. So in this example, protons, neutrons, electrons are all 6 for this atom of carbon. And to find the mass number, I've simply added together the protons and the neutrons. Remember, we don't count electrons toward mass number because their mass is so small that it doesn't get counted. So 6 protons, 6 neutrons, a mass number of 12 AMUs, we'd call it carbon-12. If I made that number of neutrons 7, for example, a different form or isotope of carbon, I would have 6 protons, 7 neutrons for a total of 13 particles with mass, and therefore a mass number of 13 AMUs. And we'd call it carbon-13. And then finally, the one that we just showed you here a moment ago, 6 protons, 8 neutrons, still 6 electrons. This would be an atom of carbon with a mass number of 14 AMUs, and we would call it carbon-14. So notice in this table, the only thing that's changed in terms of the subatomic particles and how many of them are present is the neutrons. And as that number of neutrons changes, the mass number goes up or down with it. As we add a neutron, the mass number increases correspondingly. Protons remain the same because that makes all of these atoms carbon, as that's that key identifier that gives us the atomic number. Now, what's the idea of an atom versus an ion? Atoms versus ions. Atoms are neutral particles, the way we're going to describe them here. This is not, I would say, gospel hard fact truth in terms of chemistry. It's not that everybody out there, when they say the word atom, necessarily is specifically talking about a neutral particle. But that's the way we're going to handle it in our class, just to try to be consistent and get comfortable with the idea and the differences between atoms or ions. So when you hear the word atoms, and try to use it this way too, when we use the word atoms, we're talking about a neutral particle. And in neutral, we mean the number of positive particles, the protons, is going to be equal to and balanced out by the number of electrons, those negative particles. So proton number equals electron number. And in that way, the number of positive charges are canceled out or cancel out the number of negative charges. Protons and electrons are equal, and the atom then would be neutral. Now, it's not always the case that that is going to be the situation. So if the electron number has fluctuated, we'll have a particle that no longer has a balance of protons and electrons. And so when the protons and electrons are not in balance or are not equal, we'll have an overall charged particle. Atoms can either gain electrons or lose electrons. Now you might look at that and say, hey, wait a second. Couldn't I make the particle charged by changing the number of protons too, by gaining protons or losing protons? In theory, mathematically, yes, but atoms don't lose or gain protons under normal conditions. When protons are being lost, now we're getting to nuclear chemistry. We're not going to deal with nuclear chemistry in first-year class. Okay, when radiation is being released by a substance, some of those cases, protons would be lost, and the actual identity of the element would change as a result. That's much beyond what we're talking about here. So for our purposes, to become charged, the only thing that can have changed, and this is really important, to become charged, the only thing that will have changed is the number of electrons. They can be either gained or lost. And when electrons are gained, you'll now have more negative particles than you have positive protons. More negative electrons than positive protons. And when that happens, you'll be negative overall because your negatives are greater than your positives. On the other hand, if I lose electrons, my protons will have stayed the same and my number of electrons will have decreased. So when I compare the number of protons with my now lesser number of electrons, that greater number of protons will make my particle slightly or somewhat positive in terms of its charge. So ions can be positive or negative, but the way they get there has to do with how the electrons have either been lost or gained from somewhere else. And that from somewhere else will come a little later on in the course. Okay. Protons and neutrons, again, for our purposes here, can't be lost or gained. They can be lost by simple nuclear radiation, but again, we're not getting into that here. So for our purposes, we're going to say protons and neutrons are fixed in an atom. Okay, how we kind of overall notate this, and if you're doing digital notes and you'd prefer to put this picture into your notes, you can go to the short URL there in the corner and download this particular image file that I created with this information around it, so you don't have to try to draw this into a Google Doc or something. So you can get that clip art there. But basically you'll see in this sort of arrangement of information that the abbreviation for the element is placed there kind of as the center. We have a PD here for the element palladium. And then around it are some key pieces of information. In the bottom left corner, and that's where it always goes for our purposes here, is the atomic number. Again, that's those protons. In the top left corner is the mass number, which is a combination of protons and neutrons. And then in the top right corner is the charge, and we only typically have to show a charge if there is a charge on, say, an ion. So if I'm positive or negative, you'll need to show my charge up there in the corner with a plus number or a negative number. So protons and neutrons, again, protons and neutrons up here give us the mass number. Charge is based on protons, pardon me, I don't know what happened there, protons versus electrons. And I won't say protons plus electrons because that's not quite right. And then atomic number is simply those protons. So you see how protons is really at the heart of each of these three things. Protons, 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 in all three of those corners by themselves for atomic number, with neutrons for mass number, and compared to electrons to give us our charge if one exists in the atom. Now what about that bottom right corner? Nothing's going to be down there for now. That's where we put the numbers that tell us how many atoms we have. So like in H2O, we put a 2 down there to tell us we need 2 hydrogens. Or in sugar, C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens, tell us the quantity. So for now, we're not talking about different quantities of atoms just yet. What about a neutral atom? So just one last one. Again, that picture is available online there at the URL shown. This is for an atom of what's Sb. Well, if I look at my periodic table, that's antimony. Antimony has an atomic number of 51 and a mass number of 123. And here, no charge is shown. So if no charge is shown, I can assume that this is a neutral atom, and essentially a charge of 0 there. I wouldn't say you're wrong to put a 0 there. It's just typically a little bit more clutter, and we don't need to show the 0 there to imply that it's a 0. So 0 can be implied, whereas charges of positive or negative anything can't. So that's the basic idea of symbols, abbreviations, particles, subatomic particles, how we find mass number and atomic number, and sort of then in the symbol notation, how we put those things together to sort of very briefly, but with lots of information, display all the facts about that particular atom or ion. In the next short video, I'll take you through some examples, kind of help you dissect these symbols and how to figure them out from basic information on the sheet that I probably gave you in class, hopefully. And if you don't happen to have a copy, you can certainly follow along from there. I'll pick it up with you in that next video. Talk to you then.